Alright, so we'll start and finish not start, we'll finish Simplex today. And we have two more topics remaining. One is duality and interior point methods. So in linear programming, what have we covered in linear programming? Can somebody summarize it for me? Yes. The best way to catch someone is who's escaping, not trying to look and catch that person. Tell me, what have we covered in linear programming so far? Aviral will know, but I'll ask you. Today you're sitting in front, all homework done. Tell me, what have we covered in linear programming so far? Right? Louder, louder. This is how you talk with your friends also. You have to be more louder, more firmer. You're intelligent. Simplex. Okay. So like what Aviral said, we first started linear programming with necessary and sufficient conditions, which are the same. They were the if and only if condition. They were the 5 conditions. That is what we did. Then we came to the simplex method, and this is what we did so far in simplex. So no talking. I'm summarizing it for you only. I know this. So we started with the derivation. We told you what is a basic feasible point. We uploaded on Google Drive 3 things, that the solution of an LP lies on a feasible polytope. The vertices of that map to a basic feasible point, and so on and so forth. Then we initialized the 5 necessary and sufficient conditions. Out of that, 4 were satisfying. The non-negativity on mu was not getting satisfied. Then we came to this last week where we iterated. When we iterated, we said we're going to change one variable in the B set to become N set to become positive, and which means that it will be thrown out of the N set, go into the B set, and so on and so forth. And we derived the heart of the simplex was that expression that xb plus is equal to xb minus d times xq plus, and xq plus was minimum of xbi divided by di. That was the heart of the algorithm which we derived. Then we did an example. Then we did theory, where we had stopped last time. Theory, there were 2 parts to it. One part was that by doing this swapping, by increasing xq plus and throwing a variable out of the n into the b and throwing a b out of the n set, you're not ensuring that all your mu's are becoming positive, which you need, non-negative. You are in fact just ensuring that the function value is getting minimized, right? Which means that as you keep iterating, you will eventually run and find your solution. And the second theory part we did was, by this swapping, how do you prove that the new b or the b plus was staying non-singular? So that is where we had stopped last time. Everybody with me? You did a lab on it, you implemented in the lab. Those who didn't do it in the lab did it at home. Then we did a tutorial where you just played around with those, and we did a real life LP formulation. That is what we did so far. I've uploaded a lot of practice problems on Drive, which I'll tell you at the end of the first lecture. I've uploaded supporting material as well, which will be used in this, as well as the practice problems which you need, which will help you prepare. So today's goal is to finish this. So we'll first talk about failures of simplex. Why, for example, you would want to go to the interior point method. Then becomes the most trickier part in the simplex algorithm, is how to initialize it, how to find that vertex, how to find that basic feasible point or the B set which satisfies those 5 things. That cannot be done straight away. There are 2 phases to it. There is one phase, you solve one LP, then you bridge it to another LP, then you solve it. So we'll finish all of this today. Then what remains for you next week is the interior point methods, which is also a type of LP where you have the concept of duality. Like said, you've taken the optimization course and somebody asked you what is KKT, so you would know Karish-Kuntaka conditions. Similarly, somebody asks you what is duality, you should know what is a dual problem, which is used in another alternative to the simplex method. Why? Because simplex doesn't always work, which we'll see in a minute. And the last topic is the quadratic programming. I want to briefly touch it. So we'll do all that on Monday. We'll do a tutorial on this section on Monday. We'll do your quiz on Monday because I came to know that you're free on Monday. So we'll finish everything on Monday and not make you worry about it closer to the end. That's the plan. About the timings of Monday, we'll talk at the end of it. So we'll see whichever is convenient to you. We'll arrange it. Let me see how much I can finish today. No, not MCQ. Who gives MCQ quiz? 1 hour. You have to work it out. I mean, MCQ, then I have to create 50 questions, and then there's a tendency of you to cheat. You'll go to the bathrooms, you will talk, you'll exchange answers. I don't want all that. Yeah? No, nobody went to bathroom. Nobody went to the bathroom. No, well, look, my teaching is different from others. You would have seen my goal is not to stress you out. My goal is to make you study for the exam, which will make sure that come December and January and you forget everything about optimization, or you'll remember this 2 years later and maybe use it in your masters or your job. That is my goal. So I want you to study well. It's not about to bother you, and unless you solve the problems or do some proofs, tiny little proofs which I've told you, these things will not settle in your brain. That is what I want. MCQ is, I mean, although you may work out an MCQ, but there's a tendency to guess also and do. So we rather not do that. That's the goal. So questions are not too hard if you are following my classes, you're following the recordings, lectures. If you're not coming, those who are hearing the recording, then also it's okay. You'll be fine. Okay, let's start with the failures. So the very first failure is infeasible or unfeasible, whatever you want to call the English word for that. So if you cannot find a solution to this, so there exists no x such that ax equal to b is true or x is greater than equal to 0, then there is no point applying a simplex. The simplest of all. This is not just true for simplex, it's true for any algorithm you're trying to solve in LP. So this is failures of LP. The second problem which we talked about was an unbounded LP. So if you recall the algorithm. So the algorithm said there was initialization step, and then what you were doing was you were solving for BD is equal to AQ, where Q was the column which you, or the element in the n set which you have picked throughout. You were doing this, and then you were saying xq plus is equal to minimum of xbi divided by di. Pick that I index and call that P, and your di should be greater than 0. And then we were saying if here we had added a step that if d is all d are less than equal to 0, then we had said the problem is unbounded. So this was the initial part, and then this was the iteration which you were doing. Right, everybody recalled the algorithm. I've just briefly written. You were initializing, then you were picking a Q. If all mu's were not greater than 0, then you're solving for BD equal to 0. Then you're saying if BD is less, all B components are less than equal to 0, we're saying unbounded. So why are we saying it unbounded? So we recall we were writing xb plus is xb minus d times xq plus. This was the next step. Okay. I've not written the whole algorithm, I've just written parts of it to emphasize unboundedness. So we were saying this is unbounded. So now let's just look at it. If all D's are less than, what is XB? Strictly greater than 0. Forget about the degenerate case that there is some elements which are 0. We are just saying N has 0 and B has non-zero. Exactly. And this is less than equal to 0. What about XQ plus? All XBI's are greater than 0, DI is greater than 0 because those are the DI's you're picking. So this is greater than 0. But now you're saying that maybe there is no DI, because then you can't find DI greater than 0, you'll not be able to find this. But let's say for the sake of argument that you are able to find XQ plus which is greater than 0. So what will happen? The whole thing will become strictly greater than 0. Correct? So there will be no element which you can swap, because you wanted to make one element in this guy to be 0 and then work on it. So let's say maybe you are not following this, because if DI's are all less than equal to 0, let's say we are in this if case, then you'll not find anything. You arbitrarily, let's say you make XQ plus to be some value greater than 0. You can always do to make sure that your algorithm proceeds. All DI's turn out to be negative. I cannot find an XQ plus by this expression because I want DI to be greater than 0. There is none. I arbitrarily put some value to be greater than 0 and I let the algorithm proceed. Once I reach this step, I realize this is strictly greater than 0, this is less than equal to 0, and I made this greater than 0 because I had to make the Q1 element in the N set positive to throw it out of the N set. Right? Then the whole thing will become greater than 0, which implies that no index in B which you can make tend to 0. Not the B matrix but the B set. No index in the B set which will make it tended equal to 0. Now look at the objective function value. C transpose X C transpose X plus, we had written it down at C transpose X plus mu Q XQ plus. This is what we had written. At what stage we had written this expression? You must be wondering why I'm looking at the phone. I had 2 meetings in the morning, so I forgot my notes. I'm looking at the scanned notes and writing the expression so that I don't write them wrong. So, at what stage did we wrote this? Sorry? Ax plus is equal to Ax. When we were trying to talk about the theory, there were 2 things we were trying to talk about in the theory, right? One was showing that C transpose X plus is less than C transpose X. Remember, at that stage, the last expression which we got was this, those who were there. So now look at in this expression. So this is C transpose X. What was mu Q? Negative, right? That is how we had picked the Q. I know it has been a week, you have forgotten, but you have to recall. See your notes and recall. And what are we doing to XQ plus? To be greater than 0. What does this mean? That you can keep increasing XQ plus and make this guy tend to minus infinity. You can keep doing it, nobody's stopping you here. Right? So, because your XQ plus is free, you're making the function go towards minus infinity. Hence, the problem is called unbounded. And you cannot proceed because you cannot make any index of B equal to 0. So that's why it's an unbounded problem which cannot be solved by the simplex method. Is it making sense, guys? Okay. So the last failure, which is actually not a failure, is the degenerate LP. Okay. So what is the meaning of degenerate? Can somebody tell me? I'm just recalling what we have done earlier. Just give me a minute. Okay, so another failure is, like we said at the very start, now we're repeating in the third week, that a basic feasible point is where B has R indices, the complement of B contains active constraints. We never force that B will contain inactive constraint, because B can actually contain active and inactive both. Means X components equal to 0 or X components strictly greater than 0. But now, till the time we have derived all these steps we have done, we have always assumed that B has elements which X strictly greater than 0. Now the question comes, if the one element in the B set has an active constraint, or the respective xi becomes equal to 0, then what happens? So that is where we run into trouble in the algorithm, which I am highlighting. This was the step in the iteration step which we had already written, right? Xb plus is xb minus gxq plus. To motivate you that how do you get xq, xq plus was, you had to do min of I of di greater than 0, and this guy, है ना? That is what you had to do, and I had taken an example that assumed that all xb's are strictly greater than 0, and for the moment assume all d's are positive. Now you know that 1d, all d's cannot be less than equal to 0, 1 or 2 can be negative, 1 or 2 can be 0, but they should be at least 1 greater than 0 for it to be not unbounded. That was the B failure, right? So we had said that we're going to take ratio of this 1 over 9, 2 over 8, 3 over 10, and then we're going to pick the minimum value, which was this. This we'll define at xq plus, because it will make one element equal to 0 and the other two elements to be greater than equal to 0. Correct? This we remember. Now take the case that one element was actually equal to 0. What happens then in the algorithm? So all, since B can contain active and inactive both, we assume that it has both inactive and active variables, right? Here, constraints rather. I'm switching between constraints and variables because the constraints in an LP are x greater than equal to 0. So it's just the variable that we are looking at, whether it's active or inactive. Everybody with me? Now if it is equal to 0 and you apply this algorithm here, so xq plus would be what? 0 over 9, 2 over 8 and 3 over 12. Correct? So what will your xq plus turn out to be? 0. Which means that you had to find an xq plus which is greater than 0, but you're not getting anything. So this is called a degenerate LP. Degenerate is the English meaning, says not good or not nice. Means it doesn't mean that it's bad, it cannot be solved, it's not easily comfortable, and it's not good to work with. So there is a concept of pivoting slash cycling. The PDF for this I have uploaded it on the drive, which I'll show you at the end of this lecture. So those who are interested can go through, but this is not for exam. So what pivoting or cycling does is, before you reach a state of 0, you start shuffling the indices out from the B into the N. Try to take as many zeros from the B, move them to the N set, so that you work with a nicer problem. So we not go into this, but this is a degenerate LP which Simplex can solve, but there has to be some extra work for it. Okay. Now coming to a thought on your projects. So today after 3:30 we'll go and we'll work on the project only. There is not much to be done. So I would want to see what progress you're doing, and then we'll decide the date of your report also. So many years back there was a group who decided to do the most efficient or most efficient, I would say, or most effective implementation of the Simplex method beyond what we are doing in the class for the project. So they took all this thing and they tried to tackle the unboundedness, or they tried to tackle the degeneracy in the Simplex method, and they coded it up and they applied to the paper which they had picked up. So this is something which you can also do in case you don't want to do the interior point methods, although that we'll discuss that on Monday. You can say I'm going to handle the case of a degenerate LP and write that Simplex code. So beside those 10 lines you have seen, there will be 20 more lines of handling degeneracy in LP. So that would help actually augment your learning, the complementary learning which I'm trying to get. Is everybody okay? So that finishes the failures part. Now we'll do the starting of Simplex. Okay. So we'll do starting Simplex. So the very first thing in starting Simplex is phase 1. So the question is, why are we splitting this into two parts of doing it in two phases? And the reason for that is, if you take any standard LP, minimize C transpose X subject to Ax equal to B and X greater than equal to 0, X belonging to Rn, A belonging to R cross M and R less than M. Full row rank also. Rank of A is R, so that it is an undetermined system of equation and there are choices which you want to solve for. So it is a very hard problem to figure out that B set. You can still bang your head against the wall and figure out a feasible point by looking at this. But then figuring out a B set which has R indices, the complement has active constraint, the corresponding B matrix is non-singular, is non-trivial. So what the theory says, or what people have derived or done work on, they say we'll try to solve a problem for which we can easily guess the basic feasible point. Then we'll transition the solution of that problem to my actual problem. That is what we are doing. That's why I've written it in 3 phases. There's a phase 1 where we can easily guess the basic feasible point. Then we'll bridge it to our main problem and then solve our secondary problem, the main problem. Okay, so that is the 3 parts we'll do. So the phase 1 part, so the LP which we'll solve is the following: E transpose Z subject to A E X Z. The original LP is still this, but I am solving a slightly different LP. So where E is a vector of all ones and it belongs to R-dimensional space, capital E contains plus ones and minus ones. EII is equal to EII is equal to plus 1 if BI is greater than equal to 0, is minus 1 if BI is less than 0. And I forgot to write X comma Z are greater than equal to 0. So now compare this with your original LP. Should I erase this? You know this, right? So we can also write this in the standard form. So your original LP, let it be written. If you want to come back to this, minimize C transpose X subject to Ax equal to B, X greater than equal to 0. A is R cross N, B is R, and C is N, R is less than N, and row rank is okay. So now we'll try to write this in this LP into the standard form C tilde transpose X tilde subject to A tilde X tilde is equal to B and X tilde greater than equal to 0. What is C tilde now? Can somebody tell me? What is X tilde? Okay, let me write this. This is the LP which we are going to solve in phase 1 by Simplex, and I'll tell you how you can figure out the basic feasible point for this LP. This LP is minimizing E transpose Z. Z is an augmented variable which you have created. There was no Z in the original problem which we have created. The constraints earlier was Ax equal to B. We have added Ax plus Ez is equal to B, and X and Z are greater than 0. What is small e? It is a vector of all ones and it's r-dimensional. What is capital E? It is a diagonal matrix with plus and minus 1 on the diagonal. It is a plus 1 if the corresponding B element is positive. It's a minus 1 if the corresponding B element is negative. Everybody okay? So if this LP, I ask you to write it in this standard form, what is X tilde? XZ, good. What is C tilde? 0 and E. I am writing as a column vector because otherwise it will be written as a row vector. We write it as a transpose. And what is A tilde? AE. Everybody with me. Good. Is that clear? This is a modified LP of the standard problem which we are going to solve first. Okay. Now take a minute and tell me how you can guess the basic feasible point of this guy or this guy, which are equivalent. Guess. मुझे ना 225 पे ये खोलना पड़ेगा. I have to show them. Just remind me if I forget, है ना? This projector is working, right? I hope so, है ना? So tell me, how would you guess? Sorry? Okay, don't answer it. So besides Aviral, others think, no, at least give it a try. There are no marks for it. What do you have to do to find a basic feasible point? You have to, the very first step you have to do is find indices which are R in number. That is the very first thing of the 5 things we do. B has R indices. Complement of B has active constraint. The corresponding B matrices are non-singular. and it's feasible. Ax equal to b and x greater than 0. Those are the 5 things we have to satisfy. The starting point is to find a set of R indices. Then you worry about whether the others are satisfied or not. How many indices do we have here? Total indices we have is n plus r, right? Because x was n dimensional, we added z which has r variables. E is r dimensional, so z is r dimensional, so n plus r, and your b is still r because the number of constraints are not changing. The number of columns are changing because the variables have increased, and the A matrix is what dimension? R cross n plus r. The number of rows are the same, A tilde matrix, but the number of columns are n plus r because this is multiplied with x tilde. If you want to look at this here, this is still r, this is n plus r, this is r, and x tilde is n plus r. So the total index set you have is n plus r instead of r earlier, correct? So that instead of n earlier, sorry, I should not write too many different things. Let me just write x here. X was earlier n dimensional, now the x tilde is n plus r. B and C you can figure out from that. You can match. B is r dimensional, C is n dimensional. So I don't have to write it down explicitly. So now the concern is, out of these available n plus r indices, how many should I throw in the B set and which one should I throw in the n set? The easiest way would be to take the indices of the Z and throw them into the B set, because Z are R in dimensions. No, it's multiplied with E and E is R dimensional. So Z is R dimensional. Does it make sense? That's the most easiest thing to think about. Otherwise, you'll have to think, out of the n indices in the X set, how many should I pick? Which R should I take it out and put that in the B set? It's so difficult to figure that out. The easiest seem, take all indices of the Z and put them in the B set. Aviral was able to think. Are others able to think with me now? The easiest idea is that, I don't know whether that is giving me a basic feasible point, but we want to just follow through and check. Is that okay? So we'll say send all Z indices to the B set. So we are satisfying the first thing of the basic feasible point, which is the B set contains R indices. Correct? What was the second thing we had to check? X tilde I not belonging to the B set implies X tilde I equal to 0. Is this true? This is what we wanted to do. I'm writing it X tilde, not X, because now we are working with an augmented problem. X and Z. Everybody with me? What is X tilde I not belonging to the B set? Just the X. Correct? Because it's X and Z. Z you have taken into the B set. So X indices will go into the complement of B set. So X belonging to the B complement or belonging to the N set, or X is equal to 0. We have a flexibility here. We have no idea which one to pick what, so I'll force the X's to be equal to 0. Everybody with me? Okay, what was the third thing to check? The indices in the B set and pick the columns from the A matrix. They should be non-singular, which means that now my matrix is at A or A tilde? A tilde, and the indices belonging to the B set. Correct? Which means which matrix is this? Because E is corresponding to the Z. A is corresponding to X, E is corresponding to the Z. Everybody with me? So you have to say, or is E non-singular. हेलो, हाँ शैलेंद्र जी, सॉरी, आई नो आप लंच पे हो गए। मैंने कहा आप 2:30 पे आ रहे हो ना फिर L34 में? हाँ हाँ, कोई बात नहीं, ठीक है, थैंक यू। All right. So now is E non-singular? Why? Because it has only pluses and minus 1 on the diagonal. You compute the eigenvalues of this. Eigenvalues would be plus and minus 1. If the matrix doesn't have a zero eigenvalue, it is non-singular. So, implies E non-singular is correct. I mean, this is answered. So we were able to satisfy three things. What were the other two things? That it should be a feasible point. So we have to check for A tilde x tilde is equal to B and check for x tilde greater than equal to 0. Everybody with me? Okay. So this was what I call it as the basic part, which I usually do after checking the feasibility. But now I'm going to check the feasibility part. I'll not erase this. Just erase this part. Any doubts? Yes, yes. Okay, third point was I had to prove that from the A tilde matrix, if you pick the columns corresponding to the indices in the B set, that should form a non-singular matrix. Correct? So what is A? A tilde is A and E. Correct? What is the indices corresponding to the B set? These are all I belonging to the Z components. Now if you look at the equation, A is corresponding to X and E is corresponding to Z. So the only thing we had to show was is E non-singular. So when E is given to you as a diagonal matrix with only pluses and minus 1 on the diagonal. Now you have to show that E is non-singular. How would you show that a diagonal matrix is non-singular? You compute its eigenvalues. Eigenvalues of a diagonal matrix are the diagonal elements itself. Since all diagonal elements are positive or negative, none is zero, it is non-singular. Make sense? Everybody clear? Okay. Now we'll check the feasibility part. So the feasibility thing we had to show, the first thing in the feasibility we have to show is A tilde x tilde is equal to B. We have to show for that given x tilde. Now let's just substitute it. What is A tilde? It's A and E. What is x tilde? It's x and 0, x and z. And this is B. What is x? 0, it's the set of active constraints which are complement of the B set. So we'll substitute this. This would imply E times Z is equal to B. So what is Z? E inverse B. Yes? So this is satisfied. You were able to find an XB for which A tilde x tilde is equal to B. The X is 0 and Z is E inverse B. So this is satisfied. Yes or no? Now comes the last thing. What was the last thing? Show, I'm writing slightly smaller. X tilde is greater than equal to 0. That's a non-negativity which you have in the LP. Correct? So what is your x tilde? It is 0 and E inverse B. Is this greater than equal to 0? Sorry. Why? What is E inverse? Should I erase this part? You are comfortable, na? It's written here actually. So E was a matrix with plus ones and minus ones. The E inverse will remain a matrix with plus ones and minus ones because the inverse of a diagonal matrix is the inverse of the diagonal element. So if you have 1 plus 1, it will remain plus 1 on the diagonal. If it's minus 1, it will remain minus 1. If it was 4 on the diagonal, it will become 1 over 4 in the inverse, correct? So it will remain this, and this is multiplied with b. Now see, there was a plus 1 here. If there was a b element, this is b1 through br. So if you want to write this, this is your z, huh? So this is b1 when b1 is positive till, let's say, minus br, because br was negative. Everybody with me? There's a plus 1 when the b component was positive. There was a minus 1 when the b component was negative. So this is nothing but b1 plus b2 plus br. Because this is positive, this is negative, that's why a minus 1 came. The negative and the negative will make it positive. Everybody with me? Yes or no? So which means that z is greater than equal to 0. So hence done. So it was so easy to find a basic feasible point. Just take the augmented variable index set z and put that in the B set, and then you're done. Correct? Now you feed this problem to simplex algorithm. It will take its iterations and find a solution. So that's phase 1 done. Now the question is, you had to solve this problem, but you ended up solving this problem. So how to go from this problem to this problem? So what we're going to show is how to take the index set of this and find a basic feasible point of this when this is converged to a solution. Everybody with me? So what we'll do is, I wanted to show you some things, and we want to take a break also at 2:30. So we'll open the drive and show you the drive first. Then take a break, and Shailenji will come to take the feedback. Then we'll do the rest of the class. You can turn the projector on. You can stop the recording. Achha, it has to be stopped, yeah?
No, it can be, but then
No, let's not do it. Should I erase it?